Another thing that we need to understand is the bit depth. So as I mentioned, there are some numbers here and they would represent the audio data, but we need to decide, as I mentioned also with quantization, how to store this data. So we could use numbers with many decimal points, let's put like this, and then we need more space in memory, or as it exists in computing, there are some space in memory and we have types of data that will use different space in memory, but they would represent values from different sizes. And it's like bits, we will store bits and we can decide how many bits we are going to use to store this information. So we could use 16 bits, we could use 8 bits, we could use 2 bits, and the number of bits will have a consequence in the range. In this case here, this function can already do something what is called normalization. So we have, for example, values that goes from minus 2 to the power of 3 until 2 to the power of 3. So it goes, let's call it minus 8 to 8, just an example. And then it will normalize and will map this range into from minus 1 to 1. So this is special because we are using this function. So it already do a lot of things for us, but we need to pay attention on the bit depth of our audio data. So here, as I mentioned, audio is typically recorded at 8, 16, and 24 bit depth, which is a theoretical maximum signal to noise quantization, signal to quantization noise ratio for a pure sine wave of approximately 43 dB. So don't worry, we will talk about dB later, we'll have a revision about dB, we'll talk about signal to noise ratio, maybe later we'll talk about quantization, but typical values you're going to find is 8, 16, and 24 bits. Going back to our analog to digital converter, here we have, for example, a circuit. It uses some resistor ladder that we mentioned before. Then we have some comparators, and we have this 2-bit priority encoder. So as I mentioned, if we have 2-bit, we will have voltage. So the analog input voltage will be from 0 to 1 volts, and we will have some outputs at the comparator, and we have some digital outputs. So we have 2 values. So this first bit can be 0 or 1. The second bit can also be 0 or 1. So with a 2-bit, this 2 to the power of 2, we have 4 different possibilities. That means that our range will be from 0 to 4 volts. So divided by 0 to 1 volt will be 0, 0, 1 to 2 volts, 0, 1, 2 to 3 volts, 1, 0, and 3 to 4 volts, 1, 1. So this is just an example. So when we're talking about 8 bits, that means that we'll take our range and then we can divide this into 2 to the power of 8 different values. Or if we have 16 bits, then it would be 2 to the power of 16 different possibilities. One thing to have in mind is that, for example, we could have that our range is only positive, like this case. With this 2-bit, we would have a possibility to go from 0 to 4 volts. But if we have negative values from minus 2 to 2, then things are a bit different, and we have different ways how to represent negative numbers using bits. So there are different ways how to do it, but one way how to do it is to use 1 bit for the signal. So we would have the first bit would indicate, for example, if it's a plus or minus, and the rest of the bits will indicate the values. So this is one possibility. As I mentioned, we are not going to cover how to convert, but need to have in mind how this bit depth works and what it means. So in future examples, we will look exactly at bit depth, and we will take, for example, a 16-bit or an 8-bit WAV file, and we will take a look at these values without any kind of normalization. So it will be different range than from -1 to 1. In audio and also in postcode modulation, so bit depth is the number of bits of information in each sample, and it corresponds to the resolution of each sample. As I mentioned, different types of audio data uses different bit depths. So we have 16 bits for CDs, 24 bits for Blu-ray. Then the number of bits will relate to quantization error, signal to noise ratio, dynamic range, and there is the whole world of quantization. There are different, for example, floating point representation. Here we have, for example, a table with the number of bits and the signal to noise ratio that we are going to learn what does it mean, how to calculate, and here the possible integer values per sample. So if we have 4 bits, we will have 16 integer values per sample. If we have 16 bits, we will have 65,536. So this will be 2 to the power of 16. It's equal to this value here. 2 to the power of 4 is 16, and so on. The floating point is when we have decimal points, for example. So the resolution of floating point samples, it's less straightforward than integer, because the floating point values, they are not evenly in space. So for this part of the theory, when we looked at our code example, we saw sample rate, we saw the range where these values come. In the next tutorial, we are going to go a bit deeper and try different bit depths and see, not using Librosa, we are going to use something else, and then we are going to see different values here, and also we will learn a bit more to make these concepts of sampling a bit more familiar to you. That's it for this part, and next tutorial we will go through line by line of this code and go and see the Python characteristics, the Python semantics, how to, why, what does it mean, this import, what is Librosa, what kind of values are these, what is this here, well, why this is it under quotes, what's print doing, what is this IPD. So I see you next time.